Okay, welcome everyone. This is the second part of chapter 12, spatial data modeling and visualization. Today we'll have a quick look at how to visualize the dynamics of disease transmission. And we had, we already, so if you have a look at the latest video, so for the video last week, there is like a little introduction about this, how to build a small world network, which is very useful. And so then we saw how to put this into a map. And there is all the procedure in the book, so coded. It's very useful. You can just follow along, and you will be able to replicate this graph. And so we talk a bit about spatial autocorrelation, which means that points that are close to each other are more likely to obviously be correlated. And so it's like more likely that you find someone infected close to another person which is infected. So this is basically within spatial model analysis, autocorrelation is allowed. And so we actually search for the presence of autocorrelation within the environment of a moving point, because this is important. So we are not looking at fixed points, but we are looking at moving points. And so today we look at spatial proximity with crinking. Okay, crinking. Let me show you this bit here. Okay, so crinking. I'm not sure if you're seeing this. Yes. Okay. So it's a method, okay, that is used to let me read this through. Predict the value of a variable at unsampled locations based on the values at samples location. So you are basically attempting at sampling, estimating a particular phenomenon, such as the infections on the location where you don't have observations. And so here I have in the notes that you find later on, which I'm going to push later, you find the all the steps to replicate the data, and then use the GStat package in particular for step-by-step attempt getting to crinking. Okay, the first step is to perform a variogram. Okay, and this is a function that in this case I was say we are attempting to estimate the infections in points where we do not have observations. Okay, and we use in this case the temperature as a factor for influencing number of cases. First thing, we use this variogram function, which basically what does is making a model and evaluating. I have some houseworks on top of, I don't know if you can hear it. And so what does is basically estimating how this observation varies. So the variance of this of the points that we have based on temperature. And so you can, if I go to R, we can see that so I can here the data were simulated, and so I can use this variogram function. I don't know if you have any experience with that. If I do this variogram function is basically calculating the residuals, or better say how the point varies within spatial temporal environment. And so it is used with a formula, which is defined as an object, and then on a specific location. So here you can find some examples that I always go straight down to examples. Here's a type of data, and you can see that you can extract the coordinates of this data and then apply a variogram. So you can, this is basically a required step before making crinking. And as you can see here, we do this, and this V, I load the library and then run the variogram. And this V is nothing else that the estimation of the distances, okay, and the value of gamma distribution. I can specify differently, but for now, that was the most obvious things to choose. And then I fit a model, a variogram model, based on these results. So you can see this function. This is very specialized on spatial data, and this fit variogram function requires to have a variogram type of data, and basically what does it? This basically runs a model, okay, fit a model that in this case you can specify different type of models. In this case, it's specify a spherical model. Oopsie. A spherical model, but you can have different types. You can use this VGM function to specify the type of, you see, exponential, spherical, Gaussian. So you have the different type of models that you can use. And I have also built up a function that allows you to select the best one, but it is still in development. It works, but sometimes it doesn't do exactly what I expect. So it is still in the development version of the package, and in the book I haven't used it, but if you do like HM seed with R, you find this function, crinking best fit, and this function basically fit a variogram model and crinking models. We still haven't done crinking, okay? We still are at the fitting variograms models. This function select the best variogram model and then apply crinking. And so, but as I said, it is good, it is not sometimes, so it's still in development. And so we fit this this variogram model, and then we plot the result of the model. And as we can see, we have a spherical type of model line that is able to capture the variance, the semivariance, and so the distance and the semivariance within points. How the point are varies, basically. Let me show you if I change to exponential, what's happened in here, for example. So as you can see, things change it. I may think that this sounds good as well, but it depends by the type of data that you are using, and in this case, spherical, it is a good one. Okay, so let me go forward, and then we perform crinking. What is crinking? So as you can see, let's see, crinking is basically use it to predict the spatial distribution of the variable of interest across a grid of points, in this case in Central Africa. Here I've just replicated all the code which is necessary for running the gstat function, because from the gstat package, the gstat function performs crinking. Okay, let me see if I show you this in here. So here there is a bit of like, you need to know what is happening here. It says it create a gstat object, okay, but this gstat object, what does is making crinking. Exactly, you have other function that say crinking, you know, but with gstats you can basically do a universal crinking very easily without any sort of issues. And as the type of model, you use the variogram model that you have selected to be the best one, interpreting the variation of your point distribution. Even here, you need to add a formula. In this case, I change it to presence instead of cases, but it is just a matter of, you know, we are still talking about case of infections related to temperature and how they vary. And so this gstats function create an object, K, we can see here. And this output, shows this output, where you have various information about the type of distances and how these points distributes with a range and some other options. We can even see here that we have, we obviously can adjust this as we like with other options. And you can even have a look at the documentation of GSTAS. That's lots, is a world of things to learn. I'm not going to that in the too much because we don't have time. But then as we have defined our estimated parameters, we can predict our most probably, you know, where the other values could be in the location where we do not have observations. We can obviously use new data, and in this case we use the grid because as you remember, we built a grid on top of the observed points, and so we can use the predict function to predict this based on these estimated parameters on new data, and then build up a data frame. So around this, we can see that we now have a geometry. This is the variance of the point, how they varied, and these are the predicted values. Here you can see that I've selected just the infected observations and then plot them. So I use a geom simple feature. The data will be this one here that we just created, the predicted values. And we fill with the, let's have a look at this. Kpred is this simple feature. I'm going to use the predicted value here, and with points and like circle points. On top of this, let's have a look at this bit here. Okay, as you can see, this is the grid of points. Then we have these lighter points that shows the highest values of probability that our new infection could be in this area. I plot the infected on top of that. As you can see, these are the infected, so the new infection could be in these areas. Just change the color and things. And here you have sort of lowest and highest area where new infection can be. Okay, it is clear that the proportions are not correct because this is Central Africa, so quite huge territory. So this point can just be an individual because it's visually taking lots of land. But just to show the procedure of doing those things, you can then restrict the area and perform the same analysis. Within this data, this simple feature that we have predicted, we also have the variance. So how this point, yes, this is what we could expect, but we also can expect that these points can vary further. Okay, now everything changed, but let me jump into . the book. So these are the two plots. So this yellow area here are the area where, based on temperature, cases might be more likely to arise. And while this other one shows the variation of this, what are the areas where the variation is higher. And this is all around here. So we are not entirely sure what's going to happen here because we don't have any points in this location. So it's an unknown outcome area. Okay, I don't know if you like, I don't know if you have any, stop sharing for a second, if you have any questions. Or I'm just you know, completely new to this topic and you just want to have a look at it later, or you have any questions in general or anything. To me, what's happened to me when I first learned those things, it was a bit confusing thinking about a model on top of a model and top of another model. So what am I doing actually? So it was a bit like, what am I doing? And so what is happening here, that you need this variogram model that basically identifies how the points, the cases, the observation that you have might vary. So the variance, in terms of variance of these points. And so what does is basically drawing a model based on variance, on your observations variance. And do you then use this model inside a crinking model to consider this important information when making a model, a spatial model? And crinking is a technique that is used to predict. Usually when you talk about spatial modeling prediction, you think about crinking. It's a technique that is it is done on a grid of points where you do not have observations, and you are basically fitting a model and considering, most importantly, considering what is the variance, what is the level of the variance of your observations, with a formula which consider factors such as, in this case, temperature. Okay, so very introduction. Then going back to here. So this is a way that allows you to understand how to visualize those things and how to customize this type of visualization. But you have other options, such as here I've, for example, added the network on top of the result. But you have a very nice and simple way to plot this with this sp-plot function. Once you have extracted the coordinates, and as you can see here, you have different areas, and those areas here, these 3 points, are the same as those ones that we found here. And so this is another way to visualize that I found it very nice as well. And you do it with one function. You don't need to customize anything. Okay, so this is the end of this chapter. You have the code for replicating everything nicely and even substitute your data and do your own analysis. And then, you know, with some extra effort, you could be very good at it and be able to visualize what it could happen in under some circumstances. So next chapter, it's advanced data visualization techniques. And here as well, the difficult part of making a book is selecting the resources, selecting the material, what I'm gonna put inside, what is the best one. So after thinking a lot, I just take a decision. Okay, I decided to put these contour plots because I found them very interesting. We haven't talked much about interactions effect within the book, but interaction effects exist. Okay, so and how and why, when to use them. And there is this kinds of plots which are amazing. So I love them. And you can visualize and see what kind of interaction your data has, like it's additive, multiplicative, and how do we make them? We always have our model and some predictors and things. And so the important part is that if we have two predictors, okay, yeah, thinking about, we have three predictors and focusing on the third one. This one, so like thinking about a very basic example, such as, I don't know, BMI and I don't know, weight, and then think about smoke, just to say out something else. Now I'm saying something else. So you want to see if smoke is interacting with, to be in some way with weights and affecting BMI, just in general. Okay, so this beta 3 is the third coefficients that you are estimating with your model. No, so it's you have the intercept, beta 1, beta 2, and beta 3. Okay, let's imagine this is one. Imagine that we have one more elements that get into model, our model. It's so adding, I don't know, such as gender or something else. When you run this model, then you have some outputs and see if beta is nearly 0, then you can think about that this interaction is additive. So, and so that means that it is just contributing to the estimation of the response value, or to the output within the other predictors. If it's negative, that is antagonist. That means that works against the others to the output. If it's greater than 0, it's synergetic, so it's fuel the increase of the output. Or if it's you know, there is this atypical situation, which is it is not 0. It is and so we can see how to visualize those things. How do we do? So I have beta 0, beta 1, and beta 2, and these are my just synthetic data. My observation are uniform, and I had some error, which is normally distributed. Okay, so first things, okay, to show you what is happening, I needed to build up something entirely. Okay, so imagine that our beta 3, it's the estimated coefficient, and it's between -10 and 200. And so this is my model, and where here I have the observed value, and I run a simple linear regression model with just 2 predictors. And here there is a first interaction between x1 and x2. And here you can see the plots that are here. Let me show you how to make this plot. There is a geom contour function. So basically what does is you have this model, you predict the new value on the model, and then create a grid of values. Okay, you can see it here. Then I basically replicate the same things for the additive and the synergistic one, and make the same plots. I show you the output. As you can see here, you have you can see that the predictions are showing these lines, where the highest values is the yellow one within the antagonistic, and the synergistic here, I can see antagonism on top of prediction here. I don't. Oh, okay. So, and this is synergistic here, where the highest value is completely on the other side. And then there is the additive, which is basically not influencing the output. So this is negative, this is positive, and this is basically just contributing null to the things. If you are able, and this is the scatter plot that shows you that this is going on this side, this is going on the other side. And so this trend here shows antagonism, this trend shows synergism. Okay. And so based on this type of visualization, you can then decide to adjust your model and add type of additive interaction, or a multiplication, which is type of interaction. So and so this is how do you do that? Is you need to have a type of data, which I shown here how to have one, and you basically need to have a grid of points, and I made a grid of points with interpolation function. So I interpolated all points to create a grid, and then create a data frame with X and Y based on this grid, in a way for you to have the all the grid of points. And then you can use this data inside a geom contour and specify that the line type need to be a factor and after stats. This is very important. The after stats and the factor here in it's very important, and even in the color. Okay, so at the end it's just this, but the important part is that you need to create the grid. Now I don't see why I have antagonist here. And so I need to fix that. Okay. Do you have any questions about this type of plots? Well, I found them first time okay, I saw in different books, but there was a future engineering, and I should have mentioned it somewhere, where I've learned how to do those things, and I think I should put that. So if you don't have any question, I can just go forward on the how to make a pyramid plot. And this is entirely different topic. And this is allows you to visualize how a population shapes within age. So each section of the population at a specific age. And this is, for example, the United Nations World Population Prospect 2002 for high-income countries, middle-income countries, and low-income countries. And you can see they shapes quite differently. And so the high-income country, like I have an higher expectation of life here, and because we are considering how the world population. Okay, so this is we have a large part of larger part of population within like certain age between 50 and 75, for example, that we don't have in lower and low income countries. So the population starts decreasing fast within age. How to make these plots is quite straightforward. It's not that difficult. You have the data. You can download the data from this package. If you want this data of the population, or you have your own. This is quite interesting because they make, you know, estimation of the population at 1 year, 5 years. It's very comprehensive resource, so you can find lots of things. And so you have a data such as this one here with the country code, the year, the age, and type of population, if it's male or female. Then here there is a quick visualization of the trend of different countries, in particular focus on the world. This is just a line plot, and you can have a look at that. But then to make a pyramid plot, what we do is basically using a geom bar with stat identity. And then this is basically it, because the data then shapes by itself. As you can see, we use the data with the year. I have reshaped the gender, the sex to be on its own vector, female and male. So I did the pivot longer and reshaped the data to have the gender to be its own vector. So then I can fill by sex. And as you can see here, we have female and male. This purple bluish thing is male, and this like reddish orangish is female. So we can see that they are similar, quite similar. The male are a bit lower. Female in high income countries, you can like see it. And so basically how to make them, once you have the data shaped this way, you use a geom bar, stats identity, and remember to fill by sex. And then something that interesting that you can animate. You can animate it. And to animate, once you have your pyramid done, you can use this GG animate function package with the transition states function, and then you need to specify a few things, like when you want to enter fade, exit fade, and so different things. Then what you will need to do is to, once you have done this, use the animate function, and you can save it as a GIF to use in your presentations. So this is all I've got for this advanced data visualization. So 2 types of plots that I found interesting to put. Nothing else. So stop sharing.